Alright, good evening. So, I guess today also no one's going to join. But anyway, what we will do is we will solve the problems, whatever I have, and you can check the YouTube videos and you can learn from there. Um, One more thing I need to share is this would be week 11, so we will be having one more session next week. So if you have any doubts, you can come back next week and you can ask me regarding the course, regarding any subjects or any course content. If you want to revisit, let me know. I will be able to revisit it. Having said that, what we are going to do today is we are going to uh, uh, similarly, I have, as we had like previous sessions, I have two questions. In one of the question is derivation. So I want to, so since this is not actually derived in the class, I thought if I derive it and I will show, if I show you something, you might better understand what a flame is and what is a self-sustaining flame, and how do you make sure that self-sustaining phenomena happens or not, and what are the different variables comes into play. So all these things, it can be analyzed. uh, so that is what we are going to do in the first question. uh, but the second question is more interesting. The second question is more or like a design problem, in which we considering the physical aspects, you have to select a equivalence ratio for which you have to run a certain experiment. We will come to the second problem sooner. First, we will solve the first one. And uh, I have gone through the assignments of week 11. It's fairly simple. I hope everyone can easily attend it. So that's why I'm not going to again do the same thing. I mean, I don't want to solve the same question again and again. It's fairly easy. uh, that's why I thought there are certain questions in the assignments which requires theoretical understanding. So that's why I thought I will show you some theoretical aspects today. And let's get started. Let me check my recordings in between. All right, it is getting recorded. All right. So what we are going to do today. So the first question says derive simplified expression for laminar flame speeds for premixed flames. Okay. Assuming one dimensional flat flame with single step kinetics, and discuss its dependence on various other variables. Okay. Um, so what this means is so question is asking us, in fact this is not a question, it's actually a concept. So it is asking us to develop a flame speed, some simplified flame speed model, uh, assuming it's a one dimensional flat flame. So basically this picture over here is misleading because we are going to deal with the flat flames. um, but it's nice, it's a nice cover page, so that's why I kept it like that. Okay, so one dimensional flat flame with single step kinetics we are going to use, and we are going to see how does the flame speed, what are the variable factors the flame speed depends on, and how it is going to alter the flame speeds. Okay, that is what we will be seeing in this first question. Okay, so for that, whenever you want to do a simplified expression, if you want to try to develop, everything starts from a basics, right? Everything starts from conservation equations. So what I'm going to do is I'm going to start from conservation equations. Across a flame, what are the variables which are conserved? Okay, so before that, let me just draw a flame. So flat flame is it, right? So let me use red color for a flame. Okay, this is the flame, straight line. And what the analysis we are going to do, the control volume we are going to take is just near the flame. Okay, this is the flame. What happens is the reactance comes and the reactance leaves. basically how let's say if you take a Bunsen burner here, the uh, the fuel and air enters, right, and then it goes here, and then it goes through the flame, and then products goes out, right. The same thing, but we have a flat burner here. Okay, so we have a flat flame here. The fuel and air, or in the sense reactants, are coming here, and the reactants are leaving over here. Okay, so that is what I drawn a simplified 1D model. Okay, here we have, this is state 1 and this is state 2, and what are the variables we have? We have row 1, and it is coming at u1, and we have row 2, row row, and it goes out at some velocity u2. Okay, and also we have only reactants entering, so mass fractions of reactants would be 1, in the sense like mass fraction of let's say fuel would be something and oxidizer would be something, but products mass fraction would be 0 in this side, and here they will be only, you will only have products. And also it enters at some t initial, ti or t1, and it leaves at t adiabatic, let's say, it has gone through the combustion process across the flow. All right, having understood the schematic, what we are going to do now is we are going to write down the conservation equations. Okay, so people also used to say this as the we call it flame centered reference or flame reference frame, right, or yeah, flame reference, and people also write it in terms of lab scale reference, which means here usually what happens, they take a tube. If they are doing such flame speed calculations, what they do is they take a tube, and they fill the fuel and oxidizer in it, and they ignite at one end, and what happens, the flame goes. So this would be like a tube. Okay, this will be filled with fuel and oxidizer, and at this point of, at this end, they will ignite. So what happens, the flame forms here, and then flame starts moving, and this is what we call it as flame speed, right, SL. So we are trying to get this flame speed, how fast the flame moves. Okay, but what we are seeing is, so this is in the lab scale reference x and y. Now what we did was we changed the reference frame. Okay, we changed the reference frame, we put it on the flame, okay, which is x dash and y dash, let's say. So basically that's what we did here. So this is x dash and this is y dash. So which means what happens, the flame sees the reactants coming towards it with the flame with the speed SL, right. So it's just coordinate transformation you need to do. You need to move your coordinate from lab scale, which is fixed reference scale, to a flame reference frame. So since flame is moving at SL, if you sit on flame and see how the reactants moves, reactants actually come towards you with certain velocity. In this case, so if you see from the lab, let's say if you sit here and then watch what happens, the flame will be moving at flame speed, right. But if you sit on the flame and see what happens, the fluid and oxidizer would be coming to you at the speed of flame speed. So that's why this u1 is actually equal to flame speed. Okay, now we need to establish the relation between SL to all other parameters or all other properties of the mixture. So it also depends on properties of the mixture, flame speed. Okay, so that is all right. So what I will do is I'll just put up this. Right. Having understood that, let's quickly write down the equations, and these equations you should already know. Um, these are governing equations. We have mass, momentum, species, and energy conservation equations. Okay, to just write one by one, and all these are at steady state. Okay, since it's in steady state, so mass conservation equation is going to be just m dot. So we are writing in terms of per unit of area because we have flat flame. We don't know what is the area is, but we can deal in terms of mass flux. So this is equal to constant, right? Which is nothing but rho u equal to constant. This is for the whole mixture. Okay, and then similarly momentum conservation equation. So what momentum conservation equation actually tells is, let me write that down. So we are actually trying to find the flame speeds, okay, and it is in the deflagration limit. Okay, if you don't know what is deflagration, deflagration is nothing but the combustion reactions happening at or the flame speed is or I can say, how can I say, the rate at which the reactants are getting burned, right? That is actually less than the speed of sound. Okay, that is called deflagrations. Okay, so basically, if the flame speed is less than speed of sound, then it is called deflagration. If it is more than speed of sound, then it is called detonation. Okay, so it happens in a supersonic flow. Let's say, for example, there are a few engines, detonation engines. So I guess detonation is not really taught in this course, so it is out of scope for this course. We will stick to deflagration. So I just thought I will let you know. So the deflagration is nothing but the flame speeds are less than the speed of sound. Okay, and uh, and hence, if you write down the full momentum equation, for example, let's say put a full Navier-Stokes equation for a 1D analysis. So here we are doing 1D analysis. Let me also write that down. So what are the assumptions we make? 1D steady. These are the assumptions, and also deflagration. We are talking about deflagration. Okay, and since all these things, let's say if you write an Navier-Stokes equation for 1D and if you try to simplify it, what you actually will get is, let me write it down, you will get something like uh, some equation which you can actually simplify it to P is equal to constant. Okay, so basically what momentum equation says is the pressure does not vary that much from the from one side of the flame to the next side of the flame. Okay, that is what this momentum equation says. So that is one thing, and now we have energy equation. No, before energy equation, let's look at species conservation equation. The species conservation equation, what does it say? It's same as mass conservation, but for each and every species, right? So you will have m dot into dy I by dx, which is the flux which is entering and leaving, okay, which is equal to, and species will be added and destroyed during a combustion process, right? When a reaction takes place, reactants gets consumed and products gets produced. So there should be a mass source and sink terms, which is nothing but omega dot I molecular weight of I. Okay, and we also know that there is going to be a diffusion. If you look at it, so hydrogen and water vapor is present, let's say, it will not stay like that, right? Hydrogen will diffuse into water vapor will diffuse into hydrogen. So because of that, there will be a diffusive flux happening that we need to take care, which is nothing but dji by dx, where ji is the diffusional flux, okay, which you can read. You know how it you can use Fick's law of diffusion, Fickian diffusion, to find out how does it look. So since this is in multi-component, we will write rho d im. Okay, so for different So this DIM is actually it's nothing but diffusion of I species into the mixture. So that is how we model this. There are different ways of modeling it. This is one of the way. We are following Fickian diffusion. Okay. Um, Other than that, so this is one thing. Okay, this is species equation. We cannot simplify it even more. And then we have a energy equation. So that's it. Only these balance equations you need to make sure the you know any physical system, let it be, let's say you take a fluid mechanics, there also you do the same thing, mass and momentum you do, because energy doesn't vary that much or temperature doesn't increase or decrease during that time. So that's why you do only two conservation equations. Let's say if you go a compressible fluid, there what happens, temperature also changes, density changes, so you do mass, momentum and energy conservation. Now what we have energy also changing and species also getting added and destroyed. So that's why in a combustion you do mass, momentum, energy and species conservation equation. So at the end of the day it's all conservation equations. That is what you need to understand, and if you understand that, all the other process would be very easy. So the energy equation then becomes m dot d h sensible, these are sensible enthalpies. Okay, I am writing in terms of sensible enthalpies. The you can write in terms of total enthalpies, but what we are going to do is we will write in terms of sensible enthalpy, and the difference between so the total enthalpy contains the reference enthalpy and sensible enthalpy, right? So what is total enthalpy? H total or H, we call it H references, H reference plus H sensible, and we know this H reference is nothing but delta H naught F. There is a formation enthalpy, right? And there will be integral of sensible enthalpy is nothing but Cp dt from T ref to T. So what we do is instead of writing the energy equation in terms of total enthalpy, we will write in terms of sensible enthalpy, and this H ref or this formation enthalpy will be taken care as a source term because of reactions. Okay, so let me remove this. So how do you write? So we have the mass is getting added and destroyed, which has certain formation enthalpy. So what you have to do is you have to write omega dot I m I, right, multiplied by, okay, sorry, omega dot I. Yeah, my omega dot I is nothing but the production and destruction rate of the species, like amount of mass getting added and subtracted. Okay, and this is going to have delta H naught Fi. So you just need to multiply what you call the formation enthalpy to it, which is acting as a heat source in this combustion reaction. So I hope you understood that, and this is going to be added for all the species, and we have d by dx of, this is heat conduction. We know energy is going to dissipate through heat conduction, right? That is going to happen something like this. So the k dt by dx is I just change it to change it in terms of enthalpy. That's it, there is no difference. So alpha is k by rho cp, so h is cp t, which is nothing but sensible enthalpy is just cp integral of cp dt. If you assume cp is constant, it's just cpt. So rho is multiplied, so at the end of the day it boils down to k dt by dx. Okay, so this is diffusion term. Yeah, so this is the governing equation which you are going to use it to derive what we call the flame speeds. Okay, now the problem here is, let's say we know by just solving this equation we cannot get the flame speed directly out of it. We should you know uh, let's say if you see, because the flame speed is kind of input to the system. Flame speed is nothing but u1, velocity with which the reactants enter, right? So we have equations only for this. In addition, we are trying to get u1 from there itself. So it's actually not fully defined if you look at it. So let's say, let's see if I can explain it to you in a better manner. So what we have is, what are the number of unknowns we have? Unknowns we have is, we don't know anything about state 2, we know only about state 1, right? So we know density of 1, we know density, so we don't know density at the uh, downstream of flame, right, at the other side of the flame. What the product density is, we don't know that. And we don't know the temperature at 2, we don't know velocity at 2, and what else we don't know? We don't know y is at 2. Okay, and in addition we need to find flame speed, right? In addition, plus we don't know u1, which is also SL. Okay, so how many unknowns we have is, we have 5 unknowns, and then we have only 4 equations. So thus solving it will not give you the flame speed, it will not give you the flame speed, because it is not fully defined. So now how do we approach this problem? So basically what we said something. So basically this conservation equation is just tells something is entering, something is leaving, and in between some combustion process is happening. That is what I am modeling. So it doesn't really know what exactly happens inside. So we need to know somehow, we need to have another equation which tells what is happening inside, right? So that's, so basically this also make SL to be eigenvalue for this system, because you can let's say you select an SL, and then you can solve this equation and you can check whether it is a meaningful result or not. If you don't achieve a meaningful result, then it is not the right answer. So you need to do something called trial and error method. You need to slowly increase SL, decrease SL, so that you check whether the the conditions at the boundary conditions are satisfied, whether all the equations are satisfied or not. So that's what it makes us, that SL, you need to assume something which becomes an eigenvalue here. So SL, if you assume some SL, then you will be able to solve this, right? And if you solve this, you will get some solution, but that solution has to agree with the boundary conditions. So what we have here is, we have temperature to be, so okay, let me draw that. So what do I mean by boundary conditions? So what I have is, I have this, we call this X, and I have flame here. Okay, this is my flame. This is my flame. So let's say if I draw temperature profile, how does it look? So initially I will have low temperature, which is Ti or T1, okay, and then near the flame, because of heating, you will have little high temperature, and then after heating it's going to be very high, right? So you are going to have something like this, and after this it's going to be very high. This is going to be a T adiabatic, okay. And similarly, let's say if you draw the species conservation equation, or let's say the reactance species, so it's going to be going something like this, and then after the flame it's going to be go down. Y, what do you call, Y reactance going to be 1, and this is Y, yeah, this is what Y reactant is. So this will be 1 over here, and it will be a very less amount over here, okay. So which means I have certain boundary conditions derived, okay, at certain distance. So we don't know that distance anyway. So we have this is some distance and this is some distance. Okay, so this is whole thing is called flame thickness in between. So at one side of the flame I have Ti, at the other side of the flame I have T adiabatic. So let's say if you select some flame speed, let's say if you solve this set of equations, you will end up getting some solution which may not agree with these boundary conditions. Okay, if it doesn't agree, then that is not the correct flame speed. So that is how you need to do a trial and error analysis to get this. So but that is not what we are going to do today. We are going to use something called two zone approach. Okay, it is called two zone approach. In two zone approach, what we do is, let me draw the flame again. So we have X, we have flame over here. Okay, this is the flame. What I am going to do is, I will divide this entire zone into two separate zones. Okay, how do I do it? So this is going to be one zone, which is a preheat zone. After the flame, this is going to be, what do we call, the combustion zone or the reaction zone. Alright, so this will be preheat zone and this will be reaction zone. And the reason is, we can do some simplifications in a preheat zone which we cannot do in reaction zone, and we can do some simplification in reaction zone which we cannot do in preheat zone, so that we can arrive at another equation, so that we can close this system and we can solve and to get the flame speed. Okay, so basically what I am going to do is, let's say if I want to do this is going to be at infinity, minus infinity, and from here it's going to be, let's say, some reaction zone, some delta R, which also we don't know. Okay, now that is all right. So how this is going to help is the question we have. So let's analyze each zone separately. First is preheat zone. So the nomenclature why we made preheat zone is, so this is where combustion is going to happen, right? So near the flame the combustion is going to happen, and after the flame some reaction is going to happen, and this is going to generate lot of heat. So here we have lot of heat, and that heat, what happens, it conducts through the gas and preheats the gases which are incoming. Okay, so the heat, very high heat over here, what happens is it conducts, the conduction, based on conduction it conducts to the preheat zone. So basically whatever the fluid which is entering in the flame, it's getting preheated because of its own flame. Okay, so this is what we call it a self-sustaining flame. So it has to preheat the whole mixture which is coming in. Okay, and once it preheats, since it has a lot of energy, the energy of a mixture is above activation energy, it can react and generate and release even more energy, and that more energy will again go back and preheat the incoming mixture, and this process keeps on continuing, and that is what we call it as self-sustaining flame. And so that is what here also we are doing. To for a self-sustaining flame only we have flame speed. So we there will be lot of heat generated which heats the mixture over here, and that's why it is called preheat zone. Okay, so since it's a preheat zone, what we could do is, we can neglect reactions. We can assume reactions. This is just assumption to simplify our equations. Okay, let's assume no reactions. So if we assume no reactions, what happens to the energy equation? we have something like this, right? So dH sensible by dt equal to d by dx of rho alpha dH sensible by dx. And if you remember, we also have this delta h naught hfi h naught fi omega I dot molecular weight of I dot, right? So this part is 0 in preheat zone. That is what I'm telling. So what does this make? So one more assumption, let's say Cp is constant, or let's say effective Cp. Okay, let's say if you consider one Cp and let's say it is an effective Cp of a mixture, then if you make that assumptions, this m dot into Cp dt by dt is going to be simply alpha is going to be d by dx of times k by rho Cp times Cp times dt by dx. Okay, so all these things can get cancelled, and at the end of the day you will end up getting m dot Cp dt by dx is equal to d by dx of k dt by dx. So here k is thermal conductivity. Some people use lambda also for thermal conductivity. It's just a sign convention. All right. So one more thing, why there is this m dot double prime is coming, right? So we need, you know, uh, flame speeds. So let's say if we can write m dot in terms of flame speeds, it would be better. So what would happen to m dot? Sorry, this is happening. M dot is going to be rho 1, right? Rho unburned mixture which is coming in rho 1 times u1, which is nothing but rho 1 times SL. So we can rewrite this also as rho 1 SL Cp dt by dx is equal to d by dx of k dt by dx. All right. So now let's say you apply this for this from infinity to the to 0. Let's say this is x is equal to 0, right? So let's say for when you integrate this, you integrate this equation, integrate from minus infinity to 0, what happens is at infinity, let me see what is the temperature. Okay, I didn't draw the temperature profile. So let's say how the temperature is going to look. It's going to be something like this, right? So this is, let's say, Ti, T initial temperature, and should I write Ti? Maybe I will stick with our notation, which is T1, right? So what did I do? You see, I will stick with one notation, T1, T1. This is a T1, and then it reaches to T adiabatic on the other side. In between at the flame, what happens is it reaches some T ignition temperature, which we call it T high. Okay, so basically, let's say if I integrated from at minus infinity, I have T1, and at the flame I have Ti. Okay, and since I have that, what I can do is I can write it as rho C SL Cp dt by dx is going to be just Ti. I'm integrating. Please remember that. So this dx will come here. Basically, I do the integration. So it will be, let me show the integration so that you understand that. So integral of minus infinity to 0 rho 1 SL Cp dt is equal to integral of minus infinity to 0 d times k dt by dx. Okay, basically dx came here and I cancel the dx, that's it. So let's say if I continue this, what happens? I have SLCP. T at 0 is nothing but T ignition, minus T at T minus infinity is nothing but T1, which is going to be equal to K dt by dx at 0 minus K dt by dx at minus infinity. At minus infinity, if you look at the profile, we don't have any gradients in the temperature, right? Temperature is straight. So since we don't have gradient, this is going to be 0, because dt by dx at infinity minus infinity is equal to 0. Hence, we can rewrite this as K dt by dx. Let me write it as 0 minus, because we are coming from minus scale, is equal to rho 1 SL Cp Ti minus T1. Okay, so this is the energy equation coming out to be at the in the preheat zone. Now let's go to the reaction zone. In reaction zone, what do we do? Reaction zone is from x is equal to 0 to x is equal to delta R, right? So in reaction zone, if we look at it, the flame is going to be something like this, and I have a temperature profile which is going to be something like this. So this is going to be T1, and this is going to be some Ti, and this is going to be at T2. Now, what is the term I can neglect? It's the question. I cannot neglect reactions term, because it is reaction zone, right? If you neglect it, then whole combustion will become invalid. So I have something like m dot dh sensible by dx equal to what was the thing, minus summation of delta h naught fi omega dot I mi plus d by dx of rho alpha dh sensible by dx. So this I cannot neglect. The second term here, over here, the first term in the RHS, I cannot neglect it. The reason is simple. It's a reaction zone, and there should be something to the equation which should say, like something should say to the equation that reaction is happening. So that is coming from this term, right? We have this term and this term. Comparatively, which term would be dominant? Based on that, we can neglect the other term. So here what we have is, there is not much big difference in temperature, but there is a big difference in temperature gradient. So it was from here to here, it has gone from some value to 0 in a very short interval of length. So basically the change in temperature gradient is what more important here compared to the change in temperature over the length. So what we will do is, we will neglect this part, just neglect it, because the important thing is, so from combustion there is a lot of heat is released, and we also know that heat has to conduct to get a self-sustaining flame, and that is what we are going to do. So we are going to assume that there is heat conduction is predominant, okay, and since we do that, this term also can be reduced into, how it can be reduced, d by dx of k dt by dx is equal to minus summation of delta h naught fi omega dot I and molecular weight of I. Alright, so that is good. Now let's try to simplify this part. How would I simplify this part? Okay. So what we do is, we will assume simple single step kinetics. That's what the question also says, right? Assume a single step kinetics. Let's say, for example, I have some this mu I stoichiometric coefficient, some mu I molecular moles of I, it actually reacts and gives me something called mu I double prime m of I. This is the simple reactions, right? So then if that is the case, then how this is going to behave? Delta H naught F I omega dot I m I, we can simply write it as, this omega dot I is nothing but change in stoichiometric coefficient, which you can simply write it as H naught F I into omega dot I can be written as mu double prime mu I prime into molecular weight can be written as reaction rate. Okay, the rate at which these things are reacting is what? Nothing but the production and destruction of the species. That is what we are telling, right? So basically I replace omega dot mi into the stoichiometric coefficient difference times the reaction rate. Reaction rate gives me how much amount of reaction has progressed, right? So that is what you use to calculate production and destruction of species, and hence we can write this as, since stoichiometric coefficient is constant, in a reaction the stoichiometric coefficient is not going to vary. Like 1 mole of methane is going to react with 1 mole of air or 2 moles of air in a stoichiometric condition. So we can, if you recall it, the reaction rate, if you take it outside, the other term actually reduces into enthalpy of reactions or enthalpy of combustion, which is nothing but heating value. Okay, so this we can update in the in our equation. So how do we do it? Let me go back. This is the equation I need to substitute. Okay, so if I substitute it, I will get d by dx of k dt by dx is equal to delta HR into reaction rates. Okay, RR is reaction rate. All right, that is great. So we have simplified it to a certain extent. We assume that reaction rate is going to be, we know reaction rate, and we know that there is delta HR which is known for a mixture, and hence this actually can reduce into so this also we can again integrate it, but instead I am going to take another approach. What I am going to do is I am going to recast this first term into, so I am going to multiply k on both sides. Okay, so k times, I am going to write d by dt times dt by dx, which is d by dx, right? That is what I am going to do, or the other way around, sorry, it's going to be dt by dx times d by dt. Alright, so I just changed this x dependence to t dependence. Shortly tell why we are doing this, and then we multiply this on both sides, right? And then reaction rate. Now what happens, this is nothing but kind of a UV method, if you see. So k dt by dx into d by dt of k dt by dx. Let's say if you want to integrate it, so we have to integrate it, right? So we have to integrate it from 0 to delta R, which is nothing but where the temperature changes from Ti to T2 or T adiabatic. And similarly here also the, so let me write it down, integrate from x is equal to 0 to delta R, where T varies from T to Ti to T2. Okay, so let's say if I do that, k how do I write, k dt by dx times d times k dt by dx, because the operator is d by dt, right? So this, which is equal to k into delta HR reaction rate into dt, right? and this is going to vary from Ti to T2, Ti to T2. So now what it happens is it's like u dot du, that kind of dependence, which you actually can replace this as integral of Ti to T2, can replace this as d times k dt by dx the whole square, right? And you can multiply 1 by 2, right? This you can do. So if you expand d into k dt by dx the whole square, you will can end up getting the previous form. And so this can be replaced as k times delta HR reaction rate times dt. Now what we have to do is we have to just integrate it from I to 2, and what do we see? We have some gradient coming to the flame, or coming out of the flame, and there is some gradient which is actually 0 on the other end. That's what we see here, right? Here the dt by dx is 0, but here there is some gradient coming in. So let's say we do that. What happens? This is going to be um, 1 by 2 into k dt by dx whole square at what do you call delta r, right? Delta r minus k dt by dx whole square at Ti, which is nothing but not Ti, it's nothing but x is equal to 0 plus. This is on the other side, so that's why 0 plus, and this is going to be going to 0, and which is equal to integral of Ti to T2 k delta HR reaction rate times dt. So now your reaction rate, which is a function of temperature, is also getting handled. Here you cannot directly. So if you go here, let's say you take dx on the other side, right? So if you take dx on the other side, reaction rate is a function of temperature, and it is a function, temperature is a function of x axis, right? That we need to take care. Okay, so that's why we do this kind of manipulation in order to account for that. So since this, so finally this would become minus 1 by 2 k dt by dx whole square at x is equal to 0 plus, this is equal to integral of Ti to T2 k delta HR RR dt, and we will just rearrange it. K dt by dx x is equal to 0 plus, it's going to be square root of, there's going to be minus and minus going to go away. So there's going to be 2k minus, we will use it for delta HR RR dt integral of Ti to T2. Alright, so minus delta HR is nothing but enthalpy of combustion, so you can replace that into delta HC. Okay, let me write that down also so that it is clear. X is equal to 0 plus is equal to 2 times integral of Ti to T2 delta HC reaction rate times dt. Okay, all right, now what we have is we have some equation for the other side and some equation in this side. So now what we have to do is we have to do energy flux balance at the flame. So what is the energy flux going from this side to that side is nothing but diffusion, right? It's what happening, energy flux at interface. So we know whatever diffusion comes to the flame should leave the other flame, or whatever diffusion comes from the reaction zone to the flame will leave the other side. So basically what I am telling is d by dt of x at 0 minus is going to be k dt by dx at 0 plus. and because of that we can equate rho 1 SL Cp Ti minus T1 is equal to square root of 2 times integral of Ti to T2 lambda delta Hc Rr dt. Okay, now you can write an expression for SL. So that is what we require. That is why we started it, right? Ti minus T1. So the question is, I will leave it up to you. I will not say the answer. The question is, we started with reactions which are not full, right? So it is not fully defined. The system is not fully defined, but we were able to come up with the expression for uh, flame speed. So the question is, you can think about it. Where did we get the additional equation? Why, by doing this, we somehow came up with an additional equation. I will leave it up to you. You can find it out. How did we come up with this? Okay. So this is the flame speed. So for convenience, what people do is people just rewrite in terms of just T inlet, because flame speed depends on temperature at the inlet, and yeah, we'll see what are the things it depends on. So what people can do is they can take the rho CPTI T1 inside. Okay, SL is equal to inside the square root. We have square root. We have 2 here. If we assume that lambda is almost constant, we can put lambda bar divided by rho 1 Cp, and there should be another rho 1 Cp. I will show you delta Hc divided by rho 1 Cp. Then we have Ti minus T1. Okay, and then we have reaction rate is a function of temperature, as I said. Others are constant, right? So in fact we change the lambda is also a function of temperature, but here we changed it to lambda bar, which is effective lambda. So what we are doing here is we are doing Ti to T2, we just casted it in a different manner so that it's easy to understand. So divided by Ti minus T1. Okay. And now what actually happens is this delta Hc, okay, this delta Hc by Cp times T2 minus T1, which is enthalpy of combustion, divided by Cp times T2 minus T1 is nothing but from mass flow rate. So the amount of enthalpy of combustion which is used for increase in temperature of the mixture from 1 to 2, right? That is what it means. So this divided by this will actually give you stoichiometric coefficient of fuel divided by mass of fuel times the mass of mixture. So which is nothing but I will have stoichiometric coefficient of fuel divided by yi of fuel. Okay, it's like per fuel basis, right? So delta Hc is in terms of per fuel basis, so that's why we rewrite it like this. So let's say if we substitute it back, so this has to be, so this is Ti minus T1, but what we wrote is T2 minus T1. So if we assume that Ti is close to T2, okay, then we can if Ti is close to T2, this is one of the assumption, because ignition requires very high temperature. Another, we can make a lot of assumptions until we know what are the things is required for a flame speed, until it makes sense. Okay. So now if I substitute everything together, what I have is lambda by rho Cp, which is nothing but, sorry, not lambda, we just change it to k bar. Did I use lambda here also? Okay. So my notes, they have different convention. So k is thermal conductivity. Okay, so k by rho Cp is nothing but alpha diffusivity, So I can write this as alpha bar, so square root of alpha bar, and this is nothing but 2 times mu f by yf. There is also rho yf, and we have reaction rate bar. Basically what I did, T2 minus T1, right? And reaction rate, if you take an effective reaction rate times T2 minus T1 is going to be there. So these two will give you, so this part is actually giving you reaction rate bar, okay? And this is what the famous flame speed, expression. So this actually tells a lot of things to us. If you look at it, well, how does flame speed vary? What factors affect flame speed? Right? The first one we see here is alpha bar, thermal diffusivity. Why should a thermal diffusivity affect the flame speed? Is what the question is, right? Why would a thermal diffusivity will affect flame speed? We have alpha bar. So let's say if I increase the alpha bar, okay, if I increase alpha bar, what happens? SL will increase, which means flame speed increase. But physically, can you make sense out of it? Physically, does increasing alpha bar make sense for SL to vary? So if you think about it, the if alpha is more, which is nothing but diffusion, thermal diffusion is more, what happens at the reaction rate? You have lot of energy, it can diffuse, lot of heat can diffuse easily, it can diffuse, right? Since it can easily diffuse, the lot of energy can be used to preheat. So let's say I have 1 kg of fuel coming, I need to preheat 1 kg of fuel. When I increase the alpha, I can preheat 1.5 kg of fuel or 2 kg of fuel, which means I will supply more reactants to the flame, right? Which means I am increasing the flame speed. So that is what it means. So what it exactly means is, so this can easily diffuse heat. It can easily diffuse heat from the combustion zone for preheating. Okay, easily diffuse heat and preheat mixture. Okay, so that makes sense, right? So if alpha increases, then lot of heat diffusion is going to happen. Lot of heat diffusion will give rise to lot of increase in amount of preheating. So because of that, you have increase in flame speed. What is the other variable? We'll come to this complex thing now. Before that, we'll go to reaction rate. So why would a reaction rate depend on flame speed? That should be straightforward. So when you increase the reaction rate, your flame speed increases. The reason is that when you increase the reaction rate, you have lot of energy release, right? Increase in reaction rate means I'm doing the combustion very fast. The reactants are quickly reacting, right? So which means energy release. If it reacts quickly, the energy release is high. If the energy release is high, so again diffusion is going to happen, lot of energy is going to the preheating, so more you know uh, yes sir, so you will supply more reactants to it. So energy release is high, which means for same alpha, I'm talking about for same alpha, preheat is high. For same alpha, heat diffusion is more. Heat diffusion is more, and that is what is creating increase in flame speed. All right. So if the last term here is, we have 2 mu f by rho yf, right? So in fact 2 and mu f are constant. It is from the reactions. What we have is, we have rho and yf. Yf is also kind of it's a inlet condition. So we can ignore this 2 mu f and yf, and we can focus on this density. So how does the density affect? I have density. Density is actually rho 1, in fact rho unburned. Okay. So when I have mixture, the reactant mixture whose density is very high, right? If let's say density, increasing density. So if you increase density, what happens? It's inversely proportional. So SL will decrease. So what really is happening is, when you increase density, you have to preheat more gas, right? More gas has to preheat it, or the more amount of gas, more gas to be preheat for the same Q, right? More gas has to be preheat per unit volume. This is per unit volume. In a per unit volume, you have 1 kg of mass. Now what you have is 1.5 kg of mass. The reason is density has increased. Then you need a lot of energy to heat it up. So for the same amount of heat release, you will only heat a certain amount of uh, the mixture. So that is the reason the flame speed would be less. Okay, more gas to be preheat per unit volume, and that is the reason flame speed will go down. Okay, sorry, I written it in the opposite side. All right. So this is the important conclusion we have. How does the flame speed depend on, and what are the various factors it depends on? Now what do we do is, so what we did was, if I quickly recap, we did something called two zone approach. We divided the flame into two zones. One is reactant zone, one is preheat zone, one is reaction zone. And in the preheat zone we have energy incoming, and in the reaction zone, preheat zone requires energy from the reaction zone and it preheats. And in the preheat zone, what we did, we ignored reactions. In reaction zone, we ignored the thermal convection. Thermal diffusion is the more dominant than thermal convection. So we did this, and then we found the energy flux at the interface and we equated it to get S. Okay, that is the approach we took, and we found out that SL depends on heat diffusion and the reaction rate and the density, unburned density. Okay, so those are certain things you need to remember. And how these things depends on temperature and pressure. If let's say if you increase the temperature, if you increase the pressure, how it is going to depend on. So that is something I will leave it up to you. You can go through lectures now and to understand it even better. Okay, all right. So what we will do is we will continue with problem 2 now. Okay. Um, okay, let's continue with our question 2. So what do we have in question 2? It's really, so this question actually I came up with that to make sure you understand certain aspects of designing things. So what I have is a premixed methane air, okay, emerges from a round nozzle. So it is, now the figure is not misleading, it's more or less same. This figure is apt for this question. What we have is we have this round nozzle over here, and we have what do you call, the methane air coming out, methane air mixture. So there is a mixture missing. Okay, so let me write it down. So this is something CH4 plus R. Okay, methane air mixture is coming. We don't know equivalence ratio. It's just coming from a round nozzle. Okay, of diameter 2 centimeter. Diameter is given with a uniform velocity profile. Since it's a round nozzle. So here nozzle is a misleading. It's just round hose or something like round tube through which the methane air comes out. Okay, um, here we have uniform velocity profile. So we know that it's a round nozzle, so there will be a velocity profile, right? A parabolic velocity profile. So that we know from our fluid mechanics classes. So that velocity profile is given u naught, where this u naught is actually centerline velocity. So I forgot to mention it here. The flammability limit for this mixture methane air mixture is from 0.46 to 1.64. If the experiments require heat for 100 watt, select a mass flow rate of mixture considering the operation cost and also draw the flame shape is what we are going to do. So what I have is, let's say I have to do some experiments, and for that experiments I need some amount of heat. And how much amount of heat I require? I require 100 watts. So let me write that down. So power required is 100 watts, which is provided by this burner. Okay, provided by burner. Okay, now I need to select what should be my mass flow rate and what should be the equivalence ratio I should run with. Okay, so the flammability limits of this mixture is given, so within which you need to select a equivalence ratio. Okay, flammability limits is 0. Flammability 0.465 1.64. So I need to select a 5 in between, and I need to select a mass flow rate. What should be my velocity for which I should have a flame? Okay, so what they have given is, they have given u of r, it's a function of radius, it's going to be u naught into 1 minus r square by capital R square. Okay, and d is given, which is 2 centimeter, which is the diameter of the hose, and we have radius r, which is nothing but d by 2 is equal to 1 centimeter. This is equal to 0.01 meters. Now I'm asking operation cost, in the sense I need to spend less money. So the idea is what phi and m dot, okay, to get 100 watts, 100 watts heat. To get 100 watts heat, what should be my rate at which I should supply the fuel air mixture, and what is the equivalence ratio of that fuel air mixture? So that is the first question. And the second question is, so let's say if I supply with that, how is my flame shape is going to be in the, here, how is the flame shape is going to be above the nozzle. Okay, so first, how do we start with? Basically we have, these are the inputs, we need to select a phi, we need to select a m dot. So we will start with, what is our aim? The aim is to get power of 100 watts. And how are we getting it? Power is 100 watts. How are we getting is through combustion, right? So there's going to be reaction happening. This reaction is going to happen here, and this is going to generate large amount of heats, right? Or it generates high temperature, gases, and this high temperature gases you put it in a heat exchanger and extract the heat. 100 watts heat I require. So this let's say you take it out and put it in a heat exchanger, and then take the Q out. Okay, that's what I'm going to do. It's one means. You can take the heat out by various means. Let's say if that is what I want to do, then what is that going to depend on? It's going to depend on what is the amount of combustion, amount of combustion going to happen inside, right? Which is nothing but enthalpy of combustion. So this is nothing but m dot into what is the amount of mass required, or what is the amount of fuel air mixture I burned to generate this much amount of heat. Here, since it's in terms of watts, we will write mass flow rate. That's it. So mass flow rate times enthalpy of combustion, enthalpy of combustion or enthalpy of reaction, okay, or the heating value. That is going to be our measurement. Now you should understand that this delta HR. So let's say we will write, we are interested in m dot. M dot is nothing but P by delta HR. And one more thing is there, since you have other equipments, there's going to be some efficiency associated with it. So if you want 100 watts, you cannot run your burner, let's say, at 100 watts. Only I will run at 200 watts. Then after all these losses, you will end up having only 50 watts or 60 watts, right? So we will have some efficiency, which includes combustion efficiency also includes other losses. Okay, so let's add something like this: efficiency overall. Okay. Let's assume this overall is nothing but 0.7, 70% efficiency. Now you should understand that m dot is nothing but power divided by 0.7 times delta hr. Okay, where this delta hr is a function of equivalence ratio. What is the quantity, amount of fuel you are burning, what is the amount of air you have, and that is what is going to dictate my enthalpy of reaction, right? So this is a function of phi, this is a function of m dot. Ideally, to have to spend less, what do you have to spend less fuel because of economic reasons. What you have to do is you have to select equivalence ratio which is in the lean side, right? You need to select a lean fuel lean mixture, but that should be above the flammability limits. Okay, so let's say, so that is one thing you need to note. And the other thing is, let's say you get something like that, but you find the mass flow rate. Let's say you have phi equal to phi minimum. Phi minimum is the flammability limit, right? 0.4x. So for example, let's say if I select this phi minimum, because that is where I spend less on fuel, and now I spent less on fuel, and this will give me what it will give me. It will give me some m dots. Okay, and this m dot is nothing but rho u a. Okay, rho u naught. Let's say it's an average velocity. Let's say rho u naught a, and so this will give me u naught. U naught is nothing but m dot in m dot divided by rho a. Okay, so now u naught become a function of phi. So to have a flame, even though it's a flammability limit is there, to have a flame, what we need to satisfy, we need to have the SL to be less than the velocity of the fluid, right? If it is above that, it will quench it, right? So that is there. That is one more thing. We need to have. We need to. If not, flashback happens. You remember the flashback happens when there is a velocity of fluid is lesser. We need to have u naught to be greater than flame speed. Okay, so basically there are two criterias which has to be satisfied. One is economy, plus flammability limits. It's a optimization problem in fact. And the second is u naught to be greater than SL, and this is dictated by phi, equivalence ratio, right? Equivalence ratio, which is a function of delta hr, or delta hr, which is a function of phi, and this is going to be dictated by flame speed, right? So basically what I'm telling is, okay, this is going to be dictated by delta hr, this is going to be dictated by flame speed, which is also a function of phi. So both are function of phi. So what we have to do is two criteria to optimize. What we first need to understand is how flame speeds and the delta hr is going to vary based on phi. Okay, so let's say I have phi, I have delta hr, I have flame speeds, and I'm going to have 0.46 0.56, 0.76. Let's say I will make a 0 0.6, 0 0.8, lot of data points. 1.0, 1.2, 1 point, I guess it's 46 or something. 1.64, I guess. So 1.4, 1.64. So I have these many equivalence ratio to try out, and all these equivalence ratio is going to give me some delta HR and some flame speeds. So once you get delta HR, you get m dot, you get u naught, right? And that u naught should be greater than SL. So that is what I'm trying to say. So basically, let me write u naught, which is nothing but, how do we find u naught? We just wrote m dot by rho a, where m dot is p by 0.7 times delta HR. Okay, so let me write it that down. P by P is nothing but power. Let me put that is equal to 100 watts. It's not pressure. Please understand that. Delta HR. Okay, so 100 by 0.7 delta HR, 100 by 0.7 delta HR times rho times area of the nozzle. Okay, so this is also there. Okay, now for each and everything we should make sure. So let's say the first time when u naught is higher than SL is what we have to focus on. Okay, so we need to find, okay, how do we find for everything? First we will write a reaction. So we have methane air mixture, right? So we have CH4 plus A times O2 plus 3.76 N2, which gives me, let's say if you assume equilibrium also, you will have number of, CO2, H2O, some blah 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 blah, lot of things is going to be there. O2, H, O, OH, and so on. So it's just too much for us to compute this. So let's write what is phi. Uh, so we should directly get A, right? So A is nothing but x plus y by 4, where x is carbon, how much amount of carbon and how much amount of hydrogen, divided by 5. This is what A is. So here it is nothing but 4 by 4 is 1, 1 plus 1 is 2, so it's nothing but 2 by 5. So 5 is 1, A is going to be 2. So for a different equivalence ratio, you have to find delta HR and you have to find delta SL. Sorry, delta HR and SL. Okay. Once you find these two, you can find U naught. Once you find U naught, you will know for which U naught uh, SL is lesser, and you can select that equivalence ratio. That is how you find the operating conditions for for this kind of system. So now what we do is, we have to find flame speed. Flame speed also, finding flame speed, that's what we saw now, right? Last we have to make certain assumptions. You have to make a lot of assumptions in order to come up with a simple expression, and it depends on properties, it depends on reaction rate, depends on a lot of things, right? And if you want to solve everything by hand, it's not possible. So what we will do is, we will use Cantera to do it. So I will show you how to do it. So we will use Cantera to evaluate both of it. Okay. Now let me share my screen from here. And now, and entire screen. Sure. Okay. So this is what we did last time, right? So we did for well-stirred reactor. What we will do is we will create another file uh, called time or methane flame speed. So I hope this is clear. Maybe what I will do is I will one second. Oh, okay. So let me. Now I hope you will be able to see in video also. Uh, right. So what I will do is similarly I will just increase the. I forgot. Increase the font to let's say 26. Wonderful. So what we will borrow something from here. So we'll create gas and all over here. So at first what we need to do is we need to set up the things parameters, right? So we don't need m dot and all. We just we the same actually to find flame speeds also. You need to follow same kind of uh, setup. So first you need to create a gas which is GRA30 has methane combustion reactions. So we will use GRA30 same file, and for equivalence ratio 1 we will set up this. So this is going to be CH4 1, and O2 is 1 and N2 is 3.76, that is fine. And equivalence ratio we will have here. So ideally for equivalence ratio 1 we should have 1 mole of CH4 and 2 moles of oxygen. So let's see, let's print and see what happens. So whether this, it's better to make sure whether this is right or not. So now what I will do, I'll bring this up. Let's say if I run this, I put a breakpoint, continue. Now it has done something. So I have CH4 mass fractions, N2 mass fraction, O2 mass fraction. I guess this is right. Okay. So so we have 298 Kelvin. So do we have 298 Kelvin? Okay, we'll start from 298. Did I say 298? Yeah, we can consider it as 298 Kelvin and 1 atmospheric pressure, and we'll set equivalence ratio to be zero. 0.1. And let's say if I increase the equivalence ratio or if I decrease the equivalence ratio to 0.5, what happens is mole fraction of CH4 will, mass fraction of CH4 will decrease. See, mass fraction of CH4 become 0.55 to 0.283, which is half. That is right. Okay. Or you can simply calculate mass fraction and you can see. Or let's say how many moles we need. We have 2 moles of air, which is 2 into 4.76 plus 1 mole of methane, which is the total number of moles, and 1 divided by this is 0.095. The amount of moles I require 0.095057. So this is right. Okay. So you set up your gas phase mixture like this, and then what you have to do is you need to find enthalpy of reaction, right? So for that you need to, enthalpy of reaction is nothing but enthalpy of products minus enthalpy of reactions, or sorry, here it is enthalpy of combustion. Enthalpy of reactants minus enthalpy of products is what the heating value, right? So what I will do is I will just store enthalpy of find heating value. Okay, is nothing but first you need H of reactance. H of reactance is going to be this gas dot. We have enthalpy here, right? We can just use this enthalpy. How do I get enthalpy? It will say no, it's not there. Okay. Open the documentation. You have solutions. What you need to get is you need to get enthalpy. How do I get enthalpy? Here you will have a lot of functionalities which you can use. Okay. Reaction list, species, enthalpy. Enthalpy is getting printed, but I am not sure how to get it. Write functions. Enthalpy. So there are two enthalpies, right? So there is mass basis and the mole basis. That's what I'm checking. How do I get it? Solution. Enthalpy underscore mass. Maybe that will give you. Let's see. Enthalpy underscore mass. So object is not callable. I see. Looks like you cannot get it out, it seems. There should be some way. I'm not sure why it is not callable. Solution enthalpy. Alright, it's getting time. What we will do is I will just note it down and take the, manually I will find the difference. But I can do it here itself, but I'm not sure how to do it. There should be some way. Documentation. Physical species. Other mixture, species name, potential, element, move, report, species and species name. How come enthalpy is not here? Let me stop recording here and then I will restart as I found. Alright, actually I found the thing. It's enthalpy mass only. You no need to add this, open brackets and close brackets. So it showed that it is not callable, right? So callable, it is not callable means it is not a function. It's just float. You can just take it out. That's what it says. So and then you need to you need to equilibrate it at the same temperature. So what we will do is equilibrate, but now it is not, now we are not keeping enthalpy constant, but we are keeping temperature constant. That is what a heating value, right? So you will combust, you have a certain mixture, you will increase its you will convert it from reactant to product with a certain temperature and pressure. So that's why we use equilibrate TP. Last time we used equilibrate HP. Make sure you understand the difference between these two. So you can do this equilibrate, and then you can write H of products is equal to again gas dot enthalpy, then the heating value HV is nothing but H reactants minus H products. This is actually for joules per kg. So per kg of fuel. Okay. So when you multiply it with m dot kg per second, you will end up getting kilojoules per joules per second, which is nothing but which is what you want, right? So let me print the heating value. Heating value HV. Now let's say if I run this, then I already have a heating value which is 2760.7 joules per kg or kilojoules per kg. So let's say if I want to do it for all the 5, I will just put this inside a loop. Okay. So I need to put this whole thing inside a loop. How do I do it? For so first we need to make a array. So what is the phi array? Phi is equal to, I have numpy. Can I use numpy? Okay, we'll just use simple list. What are the phi you have? We have 4, 6, 1.6, 1.2, 1.4, 0.64. Okay, that is there, and then you just put it in the for loop for I is equal to, sorry, for I in phi maybe. How do we write it? For loop in Python. For loop in Python. So I keep forgetting the syntax because I don't really work in Python for a longer time. Okay, there is a problem here. It's not range. There's always an indentation problem with Python, so make sure you follow the indentation properly. So call it phi I. It's nothing but phi of I. Then we have to set certain parameters. So gas dot this thing, and this is going to be phi I. Heating value we need to find out. heating value is nothing but this whole thing. So for phi equal to phi heating value this much. So let's say if I divide it by 1000 so that I can have it in kilojoules per kg, which is more convenient. Okay, now we have something like this. Let me comment this out. Print everything, right? The problem, you keep shifting from MATLAB and Python. I keep forgetting. All right, so let's say if we run this, so we have certain values printed. So you see the heating value keeps increasing from 0.46 to 1, and then after 1 it keeps decreasing. That makes sense, right? So at stoichiometry you will have highest heating value. Okay, let me quickly write that down. So if we uh, why not let me find the velocity also here itself. Okay, so I printed heating value. Similarly, let me find out velocity here itself so that it will be easy for me. Velocity, I mean the full equations, will just put it over there. For that we need density of unburned mixture, so that we can get it from here. Gas dot Tp set equivalence ratio, this is going to be same. Okay, density of unburned mixture we can get it from, similarly gas dot density should give us unburned mixture, I guess. Let's see whether it does. uh, density mass. Okay, so you just need to call density mass. So to find density, so this is one thing good about Cantera, you no need to do anything, you can actually get it out. Rho is nothing but gas dot density mass. Alright, so we have rho also. Now we need to find velocity. Velocity is nothing but, which is u naught. U naught is nothing but we did right 100 by zero point 0.7. Okay, 1. Okay, everything else is in denominator, divided by rho times heating value, which is delta HR, times A. So we need to create A then. Where is A? A is nothing but math dot pi by 4d square. D square by 4. Okay. For that we need D. Okay. D is nothing but 0.01 centimeter. All right. This is system parameters. Find the heating values. Right. Have velocity. We find velocity. Okay. Uh, or which is u naught will give you just right u naught is at u naught meters per second. Let's be clear. Now if we run, we'll get u naught also 100%. So we have u naught also. Okay, now this u naught should be less than flame speeds. Now how do we find flame speed? For that we need to run a separate, or we can run here itself. So how do we construct a flame speed? So for that I already have a other uh, Python file. I will show you quickly. So the same thing, we will have gas, we will set temperature, we will set pressure, everything, and then we have something called flame object. Okay, and the flame object is nothing but free flame, which tells that this is a flame, and these are some refining criteria, because it has to, so whatever I told you before, right, we won't solve because it's an eigenvalue problem. It has to select a flame speed, it has to run and see whether it is matching or not, and then it tries to solve it properly. So now what we have here is, let me remove this. Right. What we have here is, we have some flame object we created, and then we did some criteria for it, and then transport model. So we have diffusions and thermal conductivity, right? So for that we need to select a transport model here, which is mixture average transport model, and then this f dot solve is what everything is, what it does. If it solves, f dot solve will solve. Okay, and then you can get f dot velocity will give you the velocity of the flame speed. What we will do is we will do the same thing over here. We will just copy this, we will put it in our loop. So I found velocity, I found these things. Now I need to find what do we call flame speeds. Again, if you don't understand what are these, I request you to go back to the previous lecture where I discussed how to learn about this. Basically these are classes of the Cantor app. Okay, so if you want to know more about it, you can go to the this documentation to learn more about it. Okay. Uh, Hope you guys were able to. Now we have, okay, there is width, something you need to set width. This width you just set it 1 meter. We are doing it for a per unit area basis, so we'll just set it over here. Width 1 meter. Set all of this, you will know these things. So f dot velocity is going to give you flame speeds. So I will add that also here. Right, yes, L, which is flame speed. Which is f dot velocity. Let me write it like this. So basically to find this, it will take some time. You need to be patient. So SL is equal to f dot velocity. How did we get it out from there? Dot velocity 0. I mean, why do they need to write 0? Okay, let's see what happens. Now we need to just write it down, and then let's see. Let's run this. Outer bounds for axis 0 with size 8. Okay, sorry. See, you already equilibrated it, right? So after this, if you're trying to find the flame speed, it will not find it. So what we do is we'll do it after this. I think the error is something else. Anyway, we'll come to that. Ideally this should work. Let's see. Alright, it's working. So you can have a look here. So now it will take a lot of time. It has to find flame speed, right? So for it has to start from zero, or if you give a good guess, you might be able to end up getting good. You might be end up getting faster convergence. Um, but I don't know how to give good guess. So basically, for a methane air mixture, if you look at it, it's going to have flame speeds around 40 centimeters per second, around that 39 to 40 centimeters per second. But that is for stoichiometric mixture. Um, you see, there is a certain issue. So I don't know whether you are able to see this. So let me focus on terminal. I couldn't increase the size of the terminal. Alright, so there is on input species C2H5 CH3. These things are not there, so if there is some problematic, it's there. That is fine. Okay, heating value and U naught is going back. The reason is once you find flame speed, it knows it has reached the equilibrium, so at that time you cannot find heating value. What I would do is I will create another gas. This is gas to find heating value. Okay, that it will not create any problem with that. Array 30 what we need to do is same thing like this, control C, but now it is for HP, find heating value. Okay, and you use this for H of reactance is HV. You use this, I equilibrate HV, and then after that I will again find HV, and that's how I find this. And for flame object I use gas, for heating value I use gas HV. Okay, alright, so this is it. What I will do is I will stop this, pause, stop. I will restart it, but it is going to take some time. Let's see how much time does it take. The reason is, if you are finding for one flame speed, it would be faster, but you are finding it for a lot of flame speeds here. Okay, I ran it again. Let's see. In the meantime, let me also share this screen. Share this. Share screen. Okay. Now we got proper. So heating value before also for 0.46 it was less, and we have this, and we have, so you can see here, right? So for 0.46, which is economical, like I have very less fuel, and I have only what do you call, large amount of oxidizer, which is air, which is freely available, no problem, but I am going to use less fuel. For that I need to have a very high velocity, but this velocity is not equivalent, it is not you know it is very much greater than SL, right? So it is, maybe you can do it, but so when the heating value increases, you require only less amount of mass. That is true. So that's why velocity decreases. um, Velocity decreases means mass flow rate reduces. You should have printed mass flow rate also, so that it would have been. Okay, it computed for 0.6. It has to compute for 0.8, 1, 1.2, 1.4, 1.6. That time I feel. Okay, it's already 9. So anyway, you guys are not here, so I will take some time to wrap it up. Velocity being very high than flame speed is also a problem. Velocity should be within a range. So that is what we call lift off. So we do not want lift off. So that also you need to take into account. For now, let's say if you do not take that into account, it is fine. But for the real scenario, you need to take into account of lift off, you need to take into account of flammability limits, you need to take into account of quenching. In fact, I have diameter to be 2 centimeter. You need to be you should make sure that the quenching distance is also, diameter is enough to have quenching. I mean, flashback shouldn't happen. So diameter should be, small enough to, arrest the heating, arrest the heat combustion in terms of heat diffusion. That should be there. That also we need to take care. So all these things comes into play. After equivalence ratio 1, it is very fast, so it can easily find the flame speeds. Again, if you look at it, you have highest flame speed at equivalence ratio 1, right? That also makes sense. And as because the reaction rate is going to reduce, right? If you remember what are all the things flame speed depends on, if you increase the equivalence ratio, the reaction rate is going to reduce. The reaction rate reduces, flame speed reduces. So reaction rate is going to be highest when you have a equivalent, uh, stoichiometric mixture. That is the reason you have such thing. Anyway, it is done. So what I will do is I will quickly note this down. So let me not fill delta HR, it is very big. Let me just fill flame speeds and U naughts. So flame speed for this is 2.9. Let me write it in centimeters per second. 2.96, 11.39, T 7.12, 37.7, 3.2, 13.8, and U naught is going to be, let's see, this is in 120.23, 93.47. I'm writing in terms of centimeters per second. 21.49, 58.3, 59.4, 60.5, 61.8. So it is actually decreasing and then increasing. The reason is delta H is decreasing. That is the problem, right? So if the delta H decreases, then again the mass flow rate has to increase. Mass flow rate increases, then velocity will increase. So that is what we see here. And what else is remaining? Yeah, that's it. So let me stop sharing. We took all the data from here. Stop sharing. Now let's see. So now I wrote all these numbers, the flame speeds and the U naughts. Now we need to select. So let's say if you have what I feel is, so what you need is U naught should be greater than SL. But how much greater? So here it is like 2 orders difference. So probably it will not lie in the, what do you call, it will either, it will be in a lift off region, right? So it may not cause the flame to sustain. That is the problem here. And here also it's almost the same. Here is also same. Only thing I feel is this point, this part and this part. These are comparable. You see 30, 40 and 50, right? 40 and 60. So these are comparable. Or you may need to go, in between these. So something like 1.1. These are comparable. These are very different. These are very different. So all these things can uh, create a potential problem. So you need to take care of lift off, uh, and you need to take care of, so you don't need to worry about flashback here, because u naught is always higher than the flame speed. So there is no place flame speed is higher, right? Let's say you require, instead of 100 watt, let's say you require 50 watts, then you might have, then you need less mass to, provide that 50 watt. Then you might have u not to be lesser. At that time you need to take care of flashbacks, okay, and you need to take care of quenching distance. So those things are there. So here now either we can select this, so maybe we can test these three, 0.8, 1 and 1.2. Obviously it is 1.2 is not the right choice in terms of economic reason. We don't need to run our burner at, at a fuel rich site. So that is not advisable, because you will be spending a lot of fuel. It is better to either run in 0.1 or let's say in 0.9. So maybe you can try 0.9 also, where it will become 30 and this will become, 60, something like that. So let's see what are these things is going to happen. So let's say if I use phi is equal to 1, so phi is equal to 1, the u naught is 58.3 meters per second, sorry, centimeters per second. And what is the other one? Flame speed is nothing but 37.7 centimeters per second. Okay, so basically that is actually, it's a end of the first question. You need to select somewhere in between. Okay, so this is going to be your thing, but you would avoid this, because for economic reasons. Okay, and let's say if I want to find the flame shape, right? How would a flame shape would look like? So let me draw it down. um, so I have, this is the burner, or the round nozzle in which this fluid is coming out. Let me just draw a central line over here. This is going to be R and this is going to be, Z, okay, some Z axis. And this is here is where this is just a nozzle. So here is where methane air is coming in, CH4 plus R mixture, it comes in. Okay, so let me rearrange this. So now my question is, my velocity profile is going to look like, how would a velocity vary with respect to R? So I would be 0 here, and I would reach a maximum over here, and again I'm going to go 0 over here. Okay, this is going to be my velocity profile. It's a parabolic velocity profile that we all know. So it is going to be like this, and the center line velocity is going to be u naught, right? And then here I have u is equal to 0. Okay, and now I have flame speeds. Flame speed is doesn't depend on velocity, right? Flame speed depends on temperature, pressure, equivalence ratio, that's it. So equivalence ratio is going to be uniform in the cross section. So ideally speaking, if I want to draw, let's say, how would it look? It will look something like straight line, but it is going to be lesser because we already found out it's just 37.7 meters per second. So now my question is, so here I velocity is went to 0. So ideally, if you say it should be like this, so flame speed is constant throughout the radial axis, but actually in real scenarios what happens, the reaction rate near the wall will be very less. Because of that, the flame speed actually goes to 0 near the wall. The reason is, when the radicals are produced, it goes and hits the wall and it attains 0. I mean, it attains to be, I mean, it attenuates, it doesn't go to a further reaction. So because of that, the reaction rate reduces near the walls, and because of that, the flame speed reduces to 0. So this is UR and this is flame speed profile. This flame speed profile. Now, using this information, you can actually find how would a flame look like. Let me draw a little accurately. So what we know is, what the flame will happen only when the velocity of the mixture is equal to the flame speed, right? The flame will be present only where velocity of mixture is equal to flame speed. But since velocity of mixture is higher, what happens is it forms a conical flame. That is what we say that SL is equal to U naught by sine alpha, or U by sine alpha. Is it U by sine alpha? Is it by cos alpha? So SL is going to be U. Sorry, I think I wrote it wrong. SL is going to be U sine alpha. So if that is the case, you can easily draw a flame shape over here. So let's say if I want to write it, draw a separate graph here, what happens over here. So this is you can draw it like this. So this is radial direction, okay, and this is U, okay. This is velocity profile. I'm trying to draw velocity profile. So at r equal to 0, what happens? The velocity is very high. So we have a parabolic profile which goes to 0 over here, and I am telling that the this is wall, right? At r is equal to capital R, which is wall, and I am telling that this will be 0 over here and it will remain constant. This is SL and this is U of fluid. Now using this relation, right, UL is equal to SL is equal to U sine alpha, what you can actually do is you can draw a flame. So we draw like this. Okay, this is how it looks like. Okay, now if you look at it, the U and SL over here in this region near the wall is same, correct? So since these two are same, sine alpha will be just 1, which is equal to 90 degrees. So there will be a flat flame over here in this part, and after that there is a big difference. There is a UL is greater than USL, so because of that the alpha angle keeps on changing and it actually reaches a maximum over near the center line. Okay, this is the flame shape. This is how flame shape would look. This is the shape of the flame. So basically what I'm saying is, okay, so now let's say if I do the same thing over here, what would happen? It's going to be something like this. Then similarly on the other side. Okay, this is how your flame look like. So this is how you draw a flame shape, like based on the flame speeds and also the uh, velocity with which mixture flows. So based on that you can even calculate different flame shapes. If the flame shape is something you don't understand, it's basically following this principle. Okay. um, Sometimes you will have lifted flame, you there will be something called, there will be diffusion happening, which makes this to be, which actually there might be some situation your flame speed would be something like this. So where flame speed is higher than the u, here there won't be any flame, so you will be having flame only here, which is a lift off condition, right? So there will be a lift off over here. So let's say here, everywhere, every point, the flame speed is less than the whole velocity profile. So if it is not like that, let's say you have something like this and the flame speed is over like this. Okay, so basically the flame speed won't go to zero in that case, because there is going to be diffusion and there is going to be something happen, there will be slight decrease, but it will not go to zero, because there is no wall termination over there, right? There is no wall ends over here, it doesn't extend till here. So if the flame speed is like this, then below this you cannot have a flame, so flame will be held a little above, right? So you will have something like this. So if you see a lift off condition, it is purely because the flame speed is higher, right, than the u. Okay. So I think that is what, yeah, so that is what I need to share it with you. And one more interesting thing about is this flame is, you see a blue flame whenever you have if you light up a candle, you will see a blue flame and then you will see a red flame. In fact, in Bunsen burner you will see a very big blue flame also. The reason is because it's a pre-mixed mixture. It doesn't require anything to come out. I mean, it doesn't. The reactants are not outside, so it doesn't. It can directly glow. And pre-mixed systems are, since it's well mixed, it can uh, combust with a very high efficiency. Whenever you see a blue flame, it means complete combustion has happened. Because of that, you will see a blue flame. And if there are any things left after this combustion, that will react with the air which is available outside, which then becomes a diffusion flame. The fuel will go here and the oxidizer will come and it meets at the flame, which is diffusion flame. And diffusion flame is very less efficient, uh, and it gives a less combustion efficiency, and because of that less temperature, which gives rise to red color, orange color, bright orange color, flame. That is the reason you see this. But at the center you will see blue flame, because there combustion is happening with the highest efficiency over there. Okay, so that is we discussed more about laminar premix flames today. Let's see if we can discuss something about diffusion flames tomorrow, I mean in the next week. Okay. uh, yeah, so that is what I want to do today. And if you have any doubts, you can reach out to me. Okay. And we can come back next class, and we can that so next class would be our last class. and you can come and ask if you have any doubts. Okay. All right. With this, I will stop here. See you next class.